Okay. So beyond what the introductory material we've already covered, we're going to move into one area of techniques, one area of data mining that we're going to start using to do predictions, to do just gain a better understanding, find patterns in data. Okay. Before we get there, though, I'm going to lay out some definitions and lay out some terms that we're going to use, and specifically why we're going to do some of the things we're going to do prior to actually applying data mining algorithms. So, and all of this is going to come out of Chapter 6 in the textbook. So if you want to follow along there, or if you need to refer back sometime later, Chapter 6 is where all of this information is going to come from about data mining. So in data mining, what we're trying to do is just find and identify patterns in large collections of data. And it's structured data in the sense that we're going to take data, for example, if we want to take data about students in this class or across different classes or all of OC. Okay? And for every student, we'll have the same information. Your name, maybe your gender, your GPA, how many hours you're taking, how many hours you've completed, and so forth. And maybe one of the pieces of information we have historically is whether or not a student graduated, okay, or didn't graduate, right? Either they dropped out or couldn't graduate or whatever happened. And now we're going to use that structured data about all these students to try to find some patterns, either to help us understand better what kind of students don't graduate and versus what kind of students do, or we might use that to make predictions. So now we have current students like you sitting in this class, and we want to try to find a pattern in all the students from the past to figure out, okay, which of you are in danger of maybe not graduating based on your characteristics being similar to the characteristics of students in the past who didn't graduate. And maybe we can use that information to make decisions about how to increase the likelihood that you would graduate, or what things we can do to help you to graduate where we think you might not otherwise. Okay, that's the kind of problem or the kind of situation data mining is going to be useful in. So a structured data set where you have what we're going to call records. In Excel, there'll be rows of data, and each record is, for example, a different student. Okay, so it's a different item in the data set. For each record, we'll have the same set of fields or the same set of characteristics that we know about them. So for a student, again, we know your name, we know your gender, we know your GPA, we know how many hours you've taken, and so forth. Each of those pieces of information we'll call a field. So many students, which are records, a few dozen maybe fields, which are characteristics of those records, and we have values for each field for every record. So we know for each student what value they have in terms of what name they have, what GPA they have, and so forth. Now, generally speaking, we're going to classify data in two different cases. One we'll call categorical data, which is data that is just names of different categories. So for example, gender. There are two genders, right? They just have names, male and female, right? There's no inherent value to one over the other. There's no inherent order to them or anything like that. They're just different classes, right? And you're in one class and only one class, right? So every student is one and only one gender, right? I hope. So that would be categorical data. Other types of data would be numeric data. So for instance, your GPA as a student is a numeric piece of data, right? It's a number, probably a fractional number of some kind, right? And probably on some scale from 0 to 4 or 0 to 5 or what scale you want to use, okay? Numeric data is special in that first, it's always ordered. That is, there's a defined inherent order to numbers, right? 1 comes before 2, comes before 3, so forth. Numeric data is also useful and different in the way that you can talk about the difference between two values on a numeric number scale, right? So you can talk about a GPA of 2 being less than a GPA of 3, but you can also infer some meaning about the difference between the two. So for example, we could say that between a GPA of 2.0 and 3.0, that difference is the same difference as a GPA of 3.0 versus 4.0, right? The difference between the two is 1 in both cases. So that's something we can say about numeric data, but not necessarily data that's categorical. For example, gender, again, there's only 2 classes, and there's no necessarily inherent definition to the difference. Another type of, or another example of categorical data might be if you wanted to classify something as low, medium, and high. Okay, those might have some kind of order to them. You might think of an order to them. Low is less than medium, is less than high. Sometimes there is an order, but there isn't necessarily meaning to the difference. That is, you can't say that low is as different to medium as medium is as different to high. Maybe that's true, maybe that's not. Categorical data has no meaning in terms of the difference between the values. They're just different or the same, and that's all you can say. Numeric values, obviously, differences have meanings. And in fact, in numeric data, we would further classify that down as interval data, in which the differences have meaning, versus ratio data, in which both differences and ratios have meaning. For example, age. You can say age is numeric data, right? A number of years old. But it's ratio data in the sense that you can say a 20-year-old is twice as old as a 10-year-old, just like a 40-year-old is twice as old as a 20-year-old, right? The fractions or the ratio between values have meaning. There's not a lot of numeric data that doesn't follow that pattern, that doesn't have meaning to ratios. The only real good example I have is temperature. So temperature data is numeric, but it's interval but not ratio numeric. That is, the ratio between values doesn't really have a set meaning for temperatures. You can't necessarily say that 100 degrees is twice as hot as 50 degrees, mainly because it depends on what scale of temperature you're talking in. That might be true in Fahrenheit, but when you convert those temperatures to Celsius, the ratio no longer is 1 to 2, or twice as hot, right? Or if you convert that to Kelvin or any other scale, right? There's not necessarily a meaning to the ratio or percentages or things like that for temperatures like there is ages. And the real important part, I guess, to know about that is for numeric data to be ratio, you have to have a defined 0 point. You have to have a point that everybody agrees is 0, and anything less than that is negative versus positive on the other side. Okay. For temperatures, again, the reason they're not ratio data is the 0 point is not necessarily defined, because Fahrenheit 0 is not the same as Kelvin 0, is not the same as Celsius 0. So there's not a set single 0 point from which you can measure all differences in ratios. Okay. Broadly speaking then, what you need to know is there's 2 types of data, categorical and numeric. Categorical are just names of categories. Technically, you could give a categorical name, which is a number, right? So you could theoretically say that you have gender 0 and gender 1, right, for male and female. Those are just names, right? Those names happen to be numbers, but that does not make the data numeric. Again, because there isn't necessarily meaning to the difference between them. I could just as easily have said the genders are 10 and 100, right? If I named males 10 and females 100 as far as a category name, that's legal, that's fine, but it doesn't make the values numeric necessarily. Does that make sense? Okay. This will come up over and over, really, when we talk about data mining. So just keep in mind 2 different kinds of data, categorical and numeric. There's a few things we need to sort of understand and talk about before we actually get into data mining. One is, in some cases, you're going to find you have missing data. That is, in some cases, you might have records for which you don't have a value for some fields. For example, you might have some students where their GPA is unknown. For some reason, that information was lost, or it wasn't recorded, or maybe it's a brand new student who doesn't really have a GPA yet, right? In most cases, data mining algorithms are going to require that it has all data, right? There's no missing pieces. So we have to kind of figure out what to do in some cases when we do have missing data. And there's really 3 different ways you can handle that. One is you could throw out the record. You could say if there's any record for which we don't know the GPA or we don't know some other piece of information, then we'll just ignore that record. We'll throw it out and not use it. Okay? And while that might make some sense, throwing away data is losing information, right? It'd be better if we could find another way to handle that. One other way we can handle that is we could just try to ignore the fact that we don't have data. Okay. Again, most data mining algorithms are going to require that data be present in every field. So we might have to just fabricate or synthesize or make up a value. So we might say we don't know the GPA for student, X, but we know a GPA for everybody else. One way we can handle that is we can just guess what his GPA would be. Maybe we'll just guess the average of all GPAs, right? Or maybe we guess the average of all similar students, same gender, same number of hours, or whatever. A lot of times, although that seems like cheating to make up information, a lot of times that's useful in the sense that data mining algorithms are really about finding patterns, okay? And even if there's a few data items that have made up or questionable values, largely speaking, there will still be a pattern in all of the data in order for that algorithm to find, right? Largely speaking, there's still going to be some patterns there that are going to be useful. So we don't want to necessarily throw away much data. It's sometimes better in the way that we can make up data. In fact, we can make up data to help identify patterns easier, or at least have patterns to find. Okay, so that's what we can do with missing data. In this class, I don't think we're going to do any examples, or there won't be any homework assignments in which you need to fabricate or handle missing data. Okay, just broadly speaking, in the real world, that may come up. That may be a problem you have to solve. Okay. Now we talked about the 2 types of data, categorical and numeric. And some data mining algorithms only work with one type of data or the other. Some data mining algorithms can work with both. But for algorithms that only, for example, can handle categorical data, then we might have to find a way to convert or transform numeric data to be categorical. Okay? For example, we might have ages of students, but we might want to use a data mining algorithm that requires that all data be categorical. So we might have to transform all the age numbers, numeric data for students, into a category. The technique we use to do that is called binning, or bucketing, where we basically say we're just going to define a range of numeric values, and any record that falls within that range, we'll put them into the same category. We'll just make up a category name for all the ages in that range. And all the ages in a different range will get a different category assigned to them, and so forth. So in that way, you're taking numeric data and assigning it to different categories based on the range of values. Okay? For example, in age, you might say anybody who's under 25 years old, we'll classify them as a young person. Right? So we're assigning a category to a whole range of age numeric values. Anybody between 25 and 45 we'll classify as middle-aged, and anybody maybe beyond that we'll classify as just older. Okay? So in that way, we took all ages, right? Any number of age values, and we put it into one of 3 categories, one of 3 categorical field values. Right? Now, obviously, you have to define what the ranges are. You have to define how many categories you want to have. I define 3 categories for age: young, middle, and old. Maybe you should define 4 or 5 or 2. The problem is there's not a right and wrong answer, right? And There's not necessarily one answer that will always be the right one or correct one, depending on the data mining algorithm you use, or depending on the amount or size of data you have, or depending on what kind of things you're wanting to data mine and patterns you're trying to find. Broadly speaking, in the real world, what you would probably want to do is try a few different techniques. Try binning or categorizing different numeric data into different numbers of categories and see what works better for your situation. In this class, at least, it will be enough to just pick and try one thing. Okay? So if you have a homework assignment in which you're applying a data mining algorithm that requires categorical data, but you have something with numeric data in it, then you can just arbitrarily pick some number of categories you want to bin that numeric data into. Okay? And I'll show you how to do that in Excel. It's literally just a few clicks of a button. Okay? And it'll do the work for you. So in this class, we're going to learn and practice the technique, but we're just going to practice it in sort of an arbitrary way, in which case you're not expected to figure out what the best thing to do is. Just find something sensible to do. Okay? However, there might be a data mining algorithm that does the exact opposite. It needs numeric data, and then you might already have categorical data. So for instance, you might have data with gender, male and female, as the two categories, but you want to apply a data mining algorithm that requires numeric data. There's, broadly speaking, two ways you can handle that, but I'm only going to teach you one as the more prevalent and generally more accepted way to do it. And that's called creating dummy variables. So that the technique for that involves, if you have a categorical data item like gender, there's two possible categories. Out of that, you can create two new numeric data fields. Okay? One of those numeric data fields we'll just call the male data field. And every record that was a male will get a value of 1 for that new field. Every value that's not male will get a 0. Okay? So this new field numeric that we've made will either have a value of 0 or 1 for every record. Okay? The ones being the ones that are males, zeros being the ones that are not. Separately, we can create basically an equivalent field for the females, where a new numeric field that takes on the value 1 for a female and 0 for a non-female or a male. Okay? That's called creating dummy variables. So we're literally creating a brand new field, one for every category, okay, from the categorical field. Any questions about that, how that works, or what the description of that is? Again, we'll show some examples. In Excel, there's some nice automated ways to do all of this. So all you have to know is if you're using a data mining algorithm and it requires one type of data or the other, and you have to transform your data, then you can use Excel, click a few buttons, and make it do the work for you. Okay? You'll just have to be the one to recognize when you have to transform data. Okay? All right. The other thing that we might want to do, it's not really a transformation, but it's something called normalization. For example, you might have, say in our students, you have two different numeric fields, one for GPA and one for age. The range of values for age is a lot larger than the range of values for GPA. That is, you might have ages from 18 all the way to 60, okay, in your student population, whereas GPA values may only range from 2.0 to 4.0, okay, a much smaller range of values. For some data mining algorithms that rely on identifying patterns based on differences in those numeric fields, a difference in age might seem bigger, right? The difference between an 18-year-old and say a 40-year-old is 22, whereas a difference between a GPA of 2 and 4 is only 2, right? So the age differences may be larger than the possible GPA differences. And some data mining algorithms might assign more value or weight to age as a result, because the differences in ages are so much greater. To overcome that, what we would do is normalize all the data. And normalization is basically trying to take data that has different numeric data, that has different ranges, and sort of squash them all down to the same range. Okay? One way you can do that, shown here on the screen, is linear scaling, where you're literally just going to transform every range or every age to a value between 0 and 1. Okay? Where 0 is the youngest person and 1 is the oldest person. So maybe 0 means age 18, 1 means age 60, and everybody else falls linearly somewhere between 0 and 1 based on where they fall in that range. Okay? In that way, if I normalize age and I normalize GPA, now if I have a person that's 18 versus 40, which is a difference of about 20 years, normalized, that will look like a difference of about 0.5, right? Somewhere in the range of that. Whereas a GPA, maybe if the GPAs range from 2.0 to 4.0, and I have a person with a 2.0 GPA and a 4.0 GPA, well, the difference when those are normalized is going to be 1, right? Because it's the difference between the minimum and the maximum. So the smallest GPA and the largest. So now, normalized, that GPA distance or difference seems more significant than the age difference, because the GPA ranged from the minimum to the maximum, whereas the age difference was really just somebody at the lower end and somebody in the middle. Okay? So normalization basically helps you make every numeric field weight or look of the same importance, regardless of how big values are or small values can get. Another way you can normalize is called using the z-score. You're not going to necessarily need to know how to do it or why it works, but it basically just says how different are you than the average. Okay, basically a percent difference than average, and it's using something called standard deviation, which mathematically you don't necessarily have to understand. So those are just two different ways you can normalize. I'll show you in Excel how you can do that. Again, in Excel, it's going to be as simple as clicking a button. It'll do the work for you. What you need to know is why we do it and when it's appropriate. And it's appropriate for data mining algorithms that assign meaning to the differences in numeric fields, and you have numeric fields that have different ranges of values. So you want to make those ranges equal. You want to scale everything to be of the same range from, say, 0 to 1 to help make them seem symmetric. Okay, so that's what we're going to have to do. So that's what we're going to learn about. From there, we're going to move on to talking about data mining itself. So data mining is finding patterns within hundreds or possibly hundreds of thousands of records. So we have records of data. Each record is structured. It has the same fields, values for the same set of fields. And what we want to find is there a pattern in those records that would help us either predict values in future records or just better understand what the patterns are and how data could be categorized and split up into meaningful subsets. So generally, we're going to use data mining for prediction purposes. Usually, what we want to do is find a pattern that helps us predict future records. So for example, if students, we might want to take past student data and use that to predict our current students, whether or not they will graduate, or maybe whether or not they pass a class, or maybe whether or not they're going to have a certain GPA minimum or something. Okay, so a predictive purpose. So there we go. Some data mining algorithms also lend themselves not just to doing prediction, but to doing gaining a better understanding. So some of these data mining algorithms are actually going to spell out what the pattern they found is. Some data mining algorithms won't be so transparent. Okay, they'll identify patterns effectively, but not in a way that we could sort of read what the pattern is or understand what the pattern is. So some of these data mining algorithms you could use not for prediction, but just to actually understand what those patterns in data are. But we have a problem. sometimes the data mining algorithm could find a pattern that exists in the data we have, but isn't necessarily a pattern that would exist in all data universally. So for example, we might take our student data and it might just happen to find that, well, 99% of all the female students happen to graduate in this set of data. So that's a pattern. But we know or could prove maybe that that's not always true. It just happened to be true in this data. Maybe there were so few female student records that they happened to all or almost all be passing or graduating. And so that was a pattern it found. But because of the lack of information or the lack of data, that's not necessarily a true pattern in the real world. So that can be a problem, especially in small data sets. And so we need to figure out a way to handle that. Now, what we call that is when a pattern is found that doesn't truly exist in the real world, we say that pattern or that was found in the noise of the data. That is, the data we used the data mining algorithm on had some flaw or anomaly in it, some sort of randomness or noise factor that the data mining algorithm found a pattern in, but isn't truly there in the real world. So we could, especially when we're predicting numeric values, the algorithm can always possibly find little tweaks it can make to predict numeric values just a little better. And in that way, it might start trying to find very specific patterns that say, well, exactly for female students with this exact GPA and this many credit hours, they always graduated. That might be true, but that may be such a small subset of the data that that's not really a useful pattern anymore. That is, you're not going to run across many students in the future that fit all of those exact criteria. In that way, we're sort of overfitting and finding too specific of patterns, okay, that aren't necessarily going to be useful. So again, that can be a problem. Generally speaking, we call this problem the problem of overfitting. That is, it's trying to fit a pattern to the data so hard that it either finds a pattern in the noise, the randomness, or it finds such a specific, minute pattern that it's not going to apply to very many data items or be very useful. So what can we do about this problem? The way we do that, the way we handle this problem, is we're going to take the data and divide it into two subsets. So we call this partitioning. We're going to name those two subsets the training data and the validation data. Okay? And broadly speaking, what we're going to do is we're going to apply the data mining algorithm on one subset, the training subset. So we're training the data mining algorithm on one subset of data, but only until it starts doing better. We're going to train it as long as it's doing better, finding better patterns on the validation data. So the data that it didn't get to identify patterns in, we want to see, do the patterns still hold in that validation data? And when you start getting an algorithm that's finding minute patterns in the training data, but those patterns aren't holding true when applied to the validation data, that's when you know you're overfitting. You're finding either patterns in the noise or minute patterns that don't necessarily help or aren't helping in real world or other data. So we're basically just splitting the data into two parts and using one part to build the algorithm or build the model, and the other part to validate that the model is still getting better and not overfitting the training data itself. Okay, again, we're going to have a button to do all this work for us. So that's the good news. But again, what you need to understand is conceptually, why do we do it? Okay, so every time we apply a data mining algorithm, especially in this class, but probably forever in your whole life, okay, you're going to first partition the data. You're going to split the data into two parts, training and validation. Because without doing that, you won't really have a way to know if you're overfitting, if you have a problem of overfitting or not. Because if you don't split the data up and you don't have data to test on versus train and build the model on, you're only building the model, you won't know if it found a good pattern or a bad pattern or a pattern that doesn't really exist or is fitting noise and randomness. Okay? So every time we do data mining in this class, we will start by partitioning the data. Okay. Beyond that, we may also need to transform data from categorical to numeric or numeric to categorical. We may need to normalize the data, okay, if we have data in different scales that we want to normalize out. But definitely, for sure, we will always partition, and this is why. All right. Some data mining algorithms are used to predict numeric field values, and we're just going to simply call that prediction. Okay. Other data mining algorithms are really trying to find values for a categorical field. It's still predicting what value a record will have, but when we use it on a categorical field, we call that classification. Those simply are just terms we use. Okay? So we will say a data mining algorithm can either be used for prediction or classification or both. Some data mining algorithms could do both. And all we're saying is whether or not they can be used to find, predict, guess a value for a numeric field versus a categorical field. And beyond that, some data mining algorithms can only use fields that have numeric data or fields that have categorical data. Okay, so this is where transformations are going to come into play. If you have a data mining algorithm that requires all fields be numeric, then you're going to have to transform any categorical fields into numeric fields first before you can apply the algorithm, or vice versa for some other algorithms. So, as we said before, we can transform back and forth. Now, how do we know when the data mining algorithm is doing good or well? How do we know when it's finding the right patterns, finding good patterns inside the data? Broadly speaking, what we'll do is we'll just use a measurement of error. That is, we will say, okay, how well, if I use this data mining algorithm and I try to use it to go back and predict each record, say of the training or validation set, how many times does it get it right and how many times does it get it wrong? Or in terms of numeric predictions, how wrong does it get it, right? So what's the average error, average percentage error, or something like that? Generally speaking, that's what we'll use. So obviously what you want is a data mining algorithm that gives a lower error, lower percentage error, or lower overall error. Another way we can sort of visualize the fit or the goodness of a data mining algorithm is a technique or a tool called a lift chart. And lift charts are sort of complex things. I'm going to try to explain it as simply as possible, but I'm going to gloss over a couple details. If you really want to understand lift charts, you can certainly go and research them more in depth. Okay, you won't need to for this class, but if you're just interested, you can. Basically, what a lift chart is trying to visualize, it's going to be a chart or a graph that's going to say how much better does the data mining algorithm do than an average guesser would. So, for example, in the student data, if I found that 90% of all students graduate, then I can build a model that just guesses everybody graduates, and I would get it right about 90% of the time, theoretically, right? So what we want to do is say, can we find a data mining algorithm that builds a model or prediction model that would do better than 90% of the time, that would have lower than 10% error? And how much lower? Okay. Effectively, that's what a lift chart is going to visualize. It's going to draw a straight line representing the average guess or the average value, and then it's going to draw another line for the data mining algorithm, and what you want to see is that data mining algorithm line be bigger or higher than the straight line. If it goes lower than the straight line, it actually means it's doing worse than an average guess. That is, if I built a data mining algorithm that guessed whether or not students graduated and it got it wrong 15% of the time, that's bad, because if I just guessed everybody graduates, I'd get it wrong only 10% of the time. So obviously I want an error less than that. So the lift chart will visualize that for us. And here's effectively what a lift chart could look like. Okay, so the red straight line there in the middle is the average guesser. That is, if I just guess the average amount, the average number of graduates, or whatever it is, that's what the red line represents. The blue line in this case represents some data mining algorithm. And what we see is that thing curves and goes higher than the red line, which is good. Yeah, is there a question?
How would a data mining algorithm guesses if a graduate is passing or failing? Is it depending on the previous study record or?
Okay, so the question, if I'm going to repeat it so I make sure I understand it. So you're saying, in my example of student records, how does a data mining algorithm guess if somebody graduates or not? So effectively what we want a data mining algorithm to do is look at the other fields of a record, what gender, what GPA, how many hours they've taken, and try to find a pattern in other data that's similar to this one, the record we want to predict, and say, okay, of those other similar records, did they graduate or not? That is, if I have a record that's a female with a GPA of 3.0 that's taken 40 hours, what are the other similar records, or what are the pattern in the rest of the records that would help me understand a female with a GPA of 3.0 with 40 hours? Do they usually graduate, or do similar people graduate or not? Yeah, so it's finding that kind of a pattern. Okay, so back to the lift chart. So the blue line represents the data mining algorithm. All you want to see is that go higher than and have a big gap between that and the red line, okay? That and the straight line. Technically, the green line would represent a perfect guesser, okay? So a perfect guesser would go as nearly straight up as it can and then just flat line, okay? Now, the reason why that is, I'm not going to get into, okay? It involves understanding some of the mathematics of why lift charts work. But just trust me when I say something like the green line that goes, it's a straight line up and then a flat line is perfect. It means it got all of the graduates correct and all of the non-graduates correct, okay? So you might think of the first part of that green line that's sort of curved, or not curved, but it's sort of going up at an angle. That's all the graduates, people who graduate. And the flat line is all the people who don't graduate. So it got them all correct in the sense that those are straight segments of the line. The blue line represents, it's sort of more curved, meaning sometimes it got some of them right, sometimes it actually guessed wrong. That is, it guessed somebody graduated when they didn't, or they didn't graduate when they did. So it doesn't move in a straight line, it's more curved or jaggedy, is what you'll see. And again, the red line is just if I guessed on average, sometimes I'd get it right, sometimes I'd get it wrong. On average, I just go up at a very gentle slope compared to the blue or green lines. Now, using lift charts, it's very simple. All you want to do is say, I want the biggest gap between the blue line, the data mining algorithm, and the red line, the guesser or average guesser line. Okay, the bigger the distance or the gap, the better it's doing. If I had two data mining algorithms and I had lift charts for each one, the way I could measure which data mining algorithm is better is which one has the bigger gap between the lines. Okay, and again, you want the blue line to be above, not below. If it goes below, it means it's doing worse than average. Obviously, that's not
good. I have a doubt, like, is the data mining refer to taking out the information or it's a kind of hidden information? We didn't define data mining in the class, right?
Okay, so the question is about whether data mining is getting information out or
the secret information or the hidden information taken out.
Right. Yeah. So data mining is about finding a pattern to the data. So do records of females usually graduate or not graduate? It would be one pattern it might find. Do males with a low GPA not graduate or graduate? Usually. Trying to find patterns like that in the example of the students. So it's trying to find what subset of information or subset of records have the same graduation value, the same either graduate or don't graduate together. That's a pattern. That would say records that follow that pattern always graduate or always don't graduate. If we can break the data into different subsets, finding that kind of a pattern, then we can use that to either predict new students, which category or which group would they fall in. We can use that to predict whether they graduate or not. Or we could just use that to understand better and say, okay, we seem to have a problem with males with a low GPA but a high number of hours taken, right? They tend to not graduate. We need to do something to help them graduate, to increase their chances. If we want more people to graduate, that's what we should focus on. So that's what we would use data mining algorithms to do, is help us identify those patterns for either predictive purposes or understanding purposes. Okay? All right.
And the percentage of failures for the data mining algorithm is the difference between the green and the blue. The percentage of errors.
So the question is the percentage of errors related to the difference between the green line and the blue line? I would say yes, with the caveat that it's more complex than that. Again, I'm not going to try to explain lift charts too much in depth. There's like a whole page or two in the textbook talking about them, and I even had to reread it about 3 times to convince myself what it meant. And then I went online and read more about it to figure it all out. They're more complex than I'm letting on. The simple answer is you just want the largest distance between the blue and red lines. In this case, the blue line being the data mining algorithm, the red line being the average. Okay, the bigger the distance, the better, above. Okay, so now let's actually talk about data mining algorithms. We're going to learn 3 different data mining algorithms. I'm going to explain roughly, generally, how they work, which is kind of useful for understanding the limitations of when they might be useful versus not. There's actually 6 or more data mining algorithms that the software we use has implemented. And I think the textbook itself goes over 6 algorithms. Once you understand these 3, you could understand any number of other data mining algorithms. Okay, you're going to basically ask the same kinds of questions of what limitations they have, how they can be used, whether they predict or classify, use numeric data, categorical data, and all that. Okay, so broadly speaking, I'm going to teach you 3 data mining algorithms. You could use that understanding to understand any number of data mining algorithms you ever want to learn about. Okay. So this is just a sampling of 3 algorithms. The first is called k-nearest neighbors. It's one of the simplest to understand algorithms out there. It is limited in the sense that it can only work with numeric data. That is, all the fields except the one you want to predict, possibly, have to be numeric. They have to have number data, not categorical name data. Okay? However, it can be used to classify or predict. So if the field that you're wanting to predict or understand the relationship between that and all other fields, that field, that target outcome field, can either be categorical or numeric. Okay? So one field can be categorical. If that's the one you want to understand, what are the patterns that help me understand what value that field has or will have in data? But everything else has to be numeric. The nice thing about k-nearest neighbors is there is only one parameter that governs how it works. Okay? So there's not a lot of knobs to tweak or special parameters to understand. There's just one, and it's just called k. Okay? And what it is will become apparent very quickly. So here's how it works. K-nearest neighbors. Basically what you want to do is you want to calculate, if you have one record that you're going to predict. Say you have one student and you're going to predict whether they graduate or not. What you're going to do is you're going to calculate the difference between that record that you're predicting, the difference between all of its fields to every other single record in the training data. So you're going to say, okay, if this student is a male, then I can compute the difference between that and every other record in terms of it's not different than the other males, and it is different than the records that are females. So it's different or not in terms of gender. In terms of GPA, it could just take the numeric difference and say if this record is a GPA of 3.5, then I can compute the difference between that and every other record, whether their GPAs are 2 or 4 or 1.5 or 2.8. I can numerically just compute the distance or difference between them. Okay? Do that for every field and for every record. Then what you want to do is select the K most similar records. That is, the K records that have the smallest cumulative difference. If I took the difference across every field, added all those differences up, what are the K records that have the smallest cumulative difference? Theoretically, those are the records that are the closest or most similar to the one I want to predict, or the one I want to understand better. Okay? So if I had a male with a 3.5 GPA, maybe he's taken 40 credit hours, I'd figure out what other K records in the training data are close to that. Other males, other students with something very close to a 3.5 GPA and with very close to 40 credit hours. Okay? Basically, those would be records similar to this one. So theoretically, they should have a similar graduate or not graduate pattern to them. Okay? So if I'm trying to predict or classify whether a student graduates or not, I'd find the K similar records to it and say, do the majority of them graduate or not? Right? If the majority of them graduate, I will assume or guess or predict that this student graduates, because his similar peers, on average, more often than not, graduated or not. Okay? So if you're trying to classify, you just take the majority. What was the majority of those K records? What was their category? That's what I'll use. That's what I'll guess. If you're trying to predict something numeric, then you can take something like an average. So I take the K nearest records and I average their value. If I'm trying to predict something like GPA, then I could average all of the K records that are close to this one, average their GPAs, and that would be my prediction. That would be my guess. Okay, that's it. That's how K nearest neighbors work. So literally, all you have to do is choose how many close neighbors or similar records do you want to use for each prediction you want to make. So here's just a visualization to help you understand that. If you have data with 3 fields, okay, we'll call it X1, field X2, and color or class, okay, then you could if X1 and X2 are numeric, which again, K nearest neighbors, you have to have numeric data, but I'm wanting to classify, so the one field that's not numeric is, say, class, and we'll represent class as either a yellow or a purple, okay, then you could literally think about graphing these, right, based on their value for X1, their value for X2. If I'm trying to predict, let's see here, if I'm trying to predict this star record, so it has some value for X2, it has some value for X1, and I want to say, do I think that is a yellow or a purple record? Then all I have to do is figure out what are the records that are very close to it. Okay? If I picked a K of 3, right, represented by this little circle here, then I would see there are 3 records, right, that are nearby. So the 3 nearest records are 1 yellow record and 2 purple records. So I would use that information to guess or predict that this star should be purple, right? Because out of the 3 nearest or most similar records, more of them are purple than not. Okay. However, if I happen to pick K of 6, I would end up with a circle radius right out there, and of those 6 neighbors, right, 4 are yellow, 2 are purple. So in that case, I might predict that the star record should be yellow, because it's out of its 6 most similar records, more of them are yellow than not. Okay. Does that make sense? Visually, that's all K nearest neighbors is doing. Now, obviously, it's doing lots of math to do differences of all pairings of certain records and all of that to figure that out. But visually, that's simply what it's doing. It's just sort of figuring out for whatever K I've selected, the parameter that I've told it I want to use, how many or what are the K most similar records in terms of cumulatively the difference between every field, and then whatever majority or whatever numeric average they have is what I'll use for my prediction or classification. Okay, let's do a quick example of K nearest neighbors. So I'm going to use Microsoft Excel. I've already installed the Analytic Solver platform software, which gives me these 2 extra tabs here at the top. one called Analytic Solver Platform, and one called Excel Miner Platform. Okay, I'm going to select the Excel Miner Platform. This is the tab you're going to use for all sorts of data mining algorithms and data mining use. Okay, so let's take as an example, this is data that was provided with the textbook for just informational purposes and example purposes. Let's take the credit. Okay, so here's a spreadsheet with records, fields, structured data. Okay, what this is, every record represents somebody who's applying to get a loan, to get credit, say from a bank. And for each of these records, or each of these people trying to get a loan, we have certain information about them represented by these different fields. Now, some of these fields have certain names which are descriptive. In the end, actually, they've been nice and actually describe in this separate sheet what each field means, what values it can take, and so forth. So, for example, this first record we have here represents somebody who's trying to get a loan for 6 months. So the duration is 6, meaning they want a 6-month loan. The new car, used car, furniture, radio, education, all of this represents what they want the loan to do, what they're trying to get the money to do. In this case, this person's trying to get the loan, I guess, to buy a radio or television, something electronic maybe, is what that represents. So literally that field has a value of 1, whereas these others have a value of 0, okay? Meaning this is the one that he's trying to get money for. The amount of the loan he's trying to get is $1,169 or euros or whatever currency this is, and so forth. So you can go through each field and figure out the meaning of each field. In the end, what we have is a field called response, which says whether or not that person was given the loan or denied the loan. So somebody given the loan has a value of 1 in that field. Somebody who was denied that loan is given a value of 0. What we're interested in doing is data mining this information to say, is there a pattern to who gets a loan and who doesn't? That is, could we predict in the future whether or not somebody should get a loan or would get a loan based on the pattern of who has and hasn't got loans in the past, based on this data here. So maybe there is a pattern that says the age of the person is a factor in whether or not they get a loan. Maybe older people get loans, younger people don't. Maybe there's a pattern that says whether or not the person is getting a large amount of a loan versus a small amount, influences whether they get the loan. Maybe there's a combination of things that say if you're an old person getting a large loan for a new car, you're likely to get the loan versus not, okay, and so forth. So that's the data mining we want to do. So we need to apply the data mining algorithm. Think back. What's the first thing we should always do before applying a data mining algorithm? Sorry?
Split the data.
Yes, split the data, or partition. So literally, once you have this software installed, Excel Miner Platform, there's a button up here called Partition, okay, which will do all the work for you. Now there's 2 options. We're always going to do the standard option, okay? It's unimportant what the other option is for this class. So we're just going to say standard partition. And once this comes up, you will see we are given the option. So it's figured out that the first row has headers, that the names of the fields. And it's just going to ask us what fields do you want to include in the partition data. In this case, I'm actually going to partition all of the data except for the first field, which is called the observation number, which if you go back and look, has a unique value for every field. It's just the number of that record. Obviously, it doesn't matter if you're applicant 1 or applicant 4,000. That's not useful in determining whether or not you get a loan or not. That was just an identifier as opposed to a person's name. It's just their number. So obviously that wouldn't be useful in prediction or finding patterns, so I'm not even going to include it when I partition the data. The only other option, well, the nice thing we see here is that there are 1,000 rows, so there's 1,000 records that we're going to split up. There's 32 fields or columns, of which I'm going to select one less, or 31 of them. And then down here you can see it's, by default, it's saying it's going to split the records into a 60% and a 40% subset. The 60% will be used to train or build the algorithm. The 40% of data will be used to validate that we're not overfitting or that we're not finding noisy patterns or patterns that don't exist in the validation set. You can change these percentages. For this class, 60-40 is as good a split as anything else. Okay? There's not a right and wrong answer. It theoretically could depend on how many records you have total. It could depend on prior knowledge about whether or not some patterns would exist in subsets of data or whatever. In this case, we're going to just always take the defaults, and it's just going to randomly put 60% of these 1,000 records in one set and the other 40% in the other set. So I'm just going to say OK. You'll see in Excel that it's actually generated a brand new sheet in the Excel sheet, or in the Excel workbook down here. So I had a sheet called data with all the raw data. It's just built a new sheet called data partition that includes the partition data. And you'll see, you can click on some links here. It'll show you all the training data, or you could click the button for validation data, which is somewhere down below that, and it would take you to that. It'll tell you here how many rows are in each set. So a 60-40 split of 1,000 records means 600 records training, 400 records validation. It'll tell you which fields you selected and so forth. Once you have this sheet, you can start running any data mining algorithm you want. Okay? Assuming you don't have to transform any data. You could just select and run algorithms, and it knows how to use training data and validation data now that it's formatted in this way. Okay, so we don't have to do any special formatting. We don't have to select anything on this sheet to know what to do. Now, for k-nearest neighbors, all the data has to be numeric, because essentially it relies on calculating numeric differences to see how different a record is from another record. In this case, we're lucky in that all of our records, or all of our fields, are numeric. Okay? Even the ones that theoretically are categorical in the sense of whether they are getting the loan for a new car or not a new car, it's already encoded that as a 0 or a 1 as opposed to yes and no. Okay? So those are already numeric in the sense that they're numbered values for those categories and so forth. So there's no transformation necessary. So all we need to do is run the k-nearest neighbors algorithm. In this case, we want to run it to do classification of the response. Okay? Now the response is also encoded as a number, 0 or 1, but what we wouldn't want to do is use a prediction algorithm, because theoretically prediction is going to predict a numeric number, which it might compute as something like 0.5 or -1, right? Which wouldn't have any meaning, because we need to know yes or no, did they get the loan. That's a categorical thing. Even though it's encoded as 0 and 1, it's categorical. So we want to use a classification form of the k-nearest neighbors algorithm. So to do that, on the data mining tab and ribbon up here, you'll see a button called Classify versus a button called Predict. Okay? Classify is when you want to classify a categorical result, like we do. So if I click that button, you'll see there's roughly 6 algorithms that can be used. Some of them have sub-options and things, but one of the 6 options is k-nearest neighbors. Okay? All I have to do is click this button. It's going to give me the option to change some parameters. Really, there's only one parameter, k, but you'll see there's some other options as well for what kind of information to generate. So here it's asking me, step one, it's telling me of the 600 training, 400 validation records, I need to know which is the variable or the field that you're wanting to classify versus all the other fields you want to look for the pattern of or pattern in. So I'm just going to find all these fields except for the response field, highlight them, click this button to make them the selected variables. So it's going to use any pattern it can find throughout all these fields of the records. And then the response I want to be the output variable. So just select it and click the arrow button. So again, any pattern in all those other fields that would help me understand or predict the response field, getting a loan or not, is what I'm doing. So once I've selected this output variable, it even tells me down here there are two classes, two categories, 0 and 1, get a loan, don't get a loan, right? For a lift chart, it specifically wants to know if you're interested in correctly predicting who doesn't get a loan or who gets a loan. So of those two categories, generally speaking, we'll just always use the 1 category. In this case, that means somebody got a loan. So the lift chart is specifically telling us how well this algorithm will do at predicting who gets loans, not predicting who doesn't get loans. Okay, slightly different thing. Okay, so once we have that, I'm going to select next. This is where we will be given the option to change the parameter k. Okay, so in this case, a k of 1 means just find the one most similar record and determine does that record get a loan or not get the loan, and use that for my classification, my guess. Now the nice thing about this software is you can actually tell it to run not just one k nearest neighbors algorithm, but run every algorithm necessary for a k between 1 and the value you specify up here, which I believe can be up to 20. So now I'm telling the algorithm, don't just run for a k of 20, try it for a k of 1, k2, k3, k4, and tell me which k parameter value gave me the best model, actually did the best job. So maybe considering 20 neighbors is too much. Maybe it finds too many records that aren't really that similar because it's looking for 20 in total, and in that way it doesn't do a very good job classifying because it starts finding two dissimilar records. Maybe k of 1 isn't good because there's a lot of records that maybe their closest record isn't the same, even though it should be, right? But a k somewhere in between 1 and 20 is good. So in this way I can find that out. I can say run k from 1 up to 20, and it'll tell me which one did best. The other thing you can do here is normalize the data, which I will do. The reason why, again, is I don't want some of these fields, like the amount of the loan, which is thousands of dollars or thousands of whatever currency, I don't want that to overshadow differences between whether you're getting the loan for a car or not a car, right? Whether you're getting it for a car or not a car is a difference of 1 because it's 0 and 1 value. Maybe you're getting the loan for, $5,000 or $5,100. In terms of loan amounts, that's not a big difference, just $100, but it's 100 times bigger of a difference than whether you're getting it for a car or not a car, right? Unless I normalize. So if by normalizing I'll make the distances or differences all of the same weight or all of the same range. So generally speaking, k nearest neighbors, you would probably always want to normalize the data. It's hard for me to imagine why you wouldn't. Yes?
What if you were trying to detect cases where there was maybe a threshold point where people aren't getting loans for cars? Maybe they're not getting loans for cars above $30,000 or something like that.
Yeah, so the question was, what if you're trying to find and identify the pattern of a threshold of amount that says anything above this amount, people aren't getting cars? That's certainly a valid pattern to look for. Unfortunately, as you're going to kind of see, k nearest neighbors wouldn't even help us know that anyway. Because of the simplicity of k nearest neighbors, just finding the k most similar records, it's not going to be able to tell us what, it's not going to verbally be able to spell out a pattern it found. Some other algorithms will and be useful for that. For k-nearest neighbors, it's just saying what are the k most similar records and what value did they have for response. So for k-nearest neighbors, it's hard to imagine why you wouldn't want to normalize. And really, k-nearest neighbors is not going to be useful to understand a pattern. It's only going to be useful to help us make a prediction. Okay.
What if we change response to the amount of 30,000? So it categorizes the k-nearest neighbors to the 30,000. So we can get to know that if the amount of 30,000 is granted or not.
So I think your question revolved around what if you were using the amount, trying to predict the amount?
Yeah.
I guess in terms of this example, I'm not sure that makes sense. You certainly could use k-nearest neighbors to predict numeric values like that.
So that way it solves his question that we can get to know if the loan is granted for amount greater than 30,000 or not.
I think so. If your question is whether or not any loans for greater than 30,000 get a loan, I think you could use not data mining, but just some filtering to filter out records and look at subsets of records to answer that question. So you wouldn't necessarily need a complex data mining algorithm to tell you that. If that's all you're interested in, you can just use Excel to do a filtering and say do out all records with an amount less than 30,000, and then just scroll through those and look for a response of 1. Yeah. Do any of them get loans? Does that make sense?
Yeah.
Okay. All right. So normalizing the data, we're going to do every k from 1 to 20. I'm going to say next. This last page is just going to give us options for what outputs we want to see. I'm going to leave the defaults as generally I would expect you probably would, to say I want to summarize the report on the training data and see a lift chart for training data, as well as summarize and produce a lift chart for the validation data. So I'll show you what all that means and what it looks like once the algorithm runs. So for 1,000 records, doing a k-nearest neighbors for k of 1, 2, 3, all the way up to 20, it ran in what, a few seconds, right? So this is what computers are good for, right? Automating numeric tasks like this one. So I'm just going to go through and briefly describe. So up front, it tells us sort of what we did. So we had these input variables. We were trying to predict or classify a response. We normalized the data. We used a k of 20, or really a k of 1 to 20, and so forth. So here it can tell, it's going to summarize basically what the data was. So 28% of the data didn't get a loan, 71% of the data did. That's just fact of the data, right? Below, it's going to tell us all the different values of k and how well they did, okay? And it's actually going to tell us which k did best in terms of the lowest percent error of validation, okay? So what this means is if I looked at 11 records, then I could predict whether or not somebody gets a loan with roughly, what, about 73.75% accuracy. That is, I get it right 73% of the time. I get it wrong 26% of the time. Okay. Now, what you will generally see probably is some k in the middle is usually better. Okay. It's very rare you would get a k of 1 or a k of 20. That's the best. Okay. Maybe in some situations. What you'll also see, just to help you understand k-nearest neighbors a little better, if I've picked a k of 1, I will always get 0% error on the training data. And the reason is because if I'm only looking for the one most similar record for a training record, in the training records, I will always just find itself, right? So I will always get it right if I use the record itself to predict its own value, right? So again, if I'm predicting who gets a loan out of the training data using the training data, and I only care about the one most similar record, it's always itself. And so I can always get it right. So don't be surprised that obviously your lowest error training or percent error training is always a K of 1, generally that will be one of your worst validation errors, right? Because usually just because that one record in the training set was good for predicting itself probably doesn't mean it's good for predicting something else in the validation set, right? Which is why we have a validation set, right? So that's what leads us here to determine a K of 11 seems optimal. Now, K of 11 seems optimal, but let's be honest, probably every record, every K in this range isn't really that much difference, right? A percent error change of 1 or less than 1, right? We're not talking about something being far superior to its peers. Any K in this basic range here seems to be doing about the same, okay? And literally, if we repartition the data in a random way, we'd get different records in the training set versus the validation set next time. Or if somebody else did this on their computer, they might literally find that a K of 9 would be better for them, right? Whereas here it just happened to work out the K of 11 was slightly better for this particular partitioning, okay? So if you happen to be comparing assignments with your neighbor for some reason, okay, again, not cheating, but just comparing, don't be surprised, you know, if they end up with a better K of something else. As long as your Ks are pretty close in percent errors, it's understandable how randomly they might, you know, get something slightly different. Okay, so that's the output. Let's look at the training charts. So there's a training chart for a lift chart for the training data. So again, you have the red line meaning the average guess. So if 76, or I think it was 74% or 71% of the records got a loan, and if we just guessed that, we'd get 70% of the records correct, right? The data mining algorithm, K-nearest neighbors, did better than that, although honestly it wasn't a lot better. I mean, the gap between these two is not a large gap. Certainly there's, you can imagine a straight line that goes all the way up and then a flat line that goes over. That would be much better than this one, okay, the blue one. So good but not great. In a separate Excel sheet, you'll see a lift chart for the validation data. And truly speaking, the validation lift chart is always the one you'd want to base your conclusion of goodness on, okay? Obviously, you could say, how well did the data do predicting itself? I mean, if it did bad at that, then it's not doing good at all, right? But what you really want to know is how well could the algorithm do predicting the validation data it hadn't seen before in terms of building the K-nearest neighbors model or the algorithm. And in that case, again, that distance is relatively small. You know, it did better than average, better than guessing would, but not much better. Okay. Any questions about that? Okay. All right. That took a little while. We're going to go over 2 more data mining algorithms, and I'll explain how they work, but then it'll be much quicker to go through running them in Excel, because now we've looked at how we do it, we've looked at lift charts. I won't have to explain that over again. So, next data mining algorithm is called classification and regression trees. Okay. As you might guess from the name alone, it can do classification. It can also do prediction. Okay, so it can be used for guessing or predicting numeric as well as categorical data. However, it does also require numeric data to do its calculations. So all the other fields have to be numeric, just like K-nearest neighbors. Okay, and it can have many parameters. We'll see that when we run the algorithm. But really, those parameters aren't really to govern necessarily how it works. It's the same basic workings. It's just to limit what it tries and what it doesn't try. It's to limit the scope of the algorithm, usually to make it run faster if you have a large set of data and you wanted to speed up how fast it took to run. You would want to limit what it does. Okay, so we'll see some of that. So here's how classification and regression trees work. Very simple. For some field, we're going to find or guess or try to find something called a split point value. So basically, if you think about the student data, we might take a look at the GPA field, and we're going to try to find a GPA value that would divide all records into the ones less than that and greater than that. So we're going to subdivide records into two categories or two subsets based on splitting them by some value for some field. Okay? And what we want to do is we want to pick a field and a split point value that divide the records into the two subsets that are the most homogeneous they can be. That is, ideally, we'd want to find a GPA that could split all records into the ones that all graduate, and the other subset are all the records that don't graduate. Right? If we could do that, then that would be the best algorithm. Right? We'd have a way to predict every record with something like 100% accuracy based on one thing alone. Usually speaking, obviously, we're not going to find such a perfect thing. So we're just going to do the best we can, pick a field and a split point value that gets us as close to homogeneous subsets as possible. And then we're going to repeat that first step again for those two subsets. So maybe we find that we can split students based on GPA, those with less than 3.0 and those with greater than 3.0. Then we're going to further look at those two subsets and say, is there a way we can split those into two subsets to try to divide out those who graduate versus those who don't? Maybe it's based on number of credit hours, those with less than 60 hours and those with greater than 60 hours. Or maybe it's based on gender, those who are females versus those who are males, whatever. We're going to keep doing that and splitting until either we found homogeneous sets, that is, all the records in some subset graduate, all the records don't graduate. Or we may quit before we get that good, because eventually, if you think about it, you can keep splitting records so many times till you're down to just one record in each subset, in which case it's by definition homogeneous because there's only one, right? So if there's only one record, then they're either all graduating or they're all not. But that's not probably a good pattern to find, because you've subdivided records into so many different categories. You're trying to find a minute, detailed pattern. All students with less than 3.0 but greater than 2.7 that are males that have less than 40 hours but greater than 39 or 38 hours, they graduate. Well, that's such a minute pattern that hardly anybody's going to follow or fit into that pattern. So it's probably not one that would be useful to understand or predict with. So the algorithm's going to split all records based on some field and split point value, and just keep doing that until it's either found homogeneous subsets or it's split the subsets into so small a section, say 10% of all records, that it's determined it's probably best not to split anymore because it's too specific at that point. So here's a visualization just to help you understand. If we start at the top and we say we have 108 records, 56 of which are pink and 52 of which are blue, whatever pink and blue mean. Those are our two categories. Then what we want to do is pick a field, maybe it's called A or whatever, and say, okay, we're going to take some field and pick a value and split everybody less than that value or everybody greater than to that value into two different subcamps. Okay, so in this case it's just represented with an A and a yes and no, but really what we'd be saying is, say, GPA is less than 3.0. Either that's true, yes, or it's not true, no. So every one of these 108 records goes either to the left or to the right. And what you see is all the records that were a yes for A generally are mostly pink, right? They're not all the pink records, because 28 records are over here that are pink, but most of all the blue ones were sort of weeded out into the right, and only few of them went over here to the left. So that's pretty homogeneous. In fact, you may want to stop there and not divide further, because at this point all these records are almost always pink, according to the pattern here. Now, for these records on the right-hand side, it's a little less homogeneous. We did get most of the blue records to over here, but we still have quite a few pink as well, so we might further subdivide based on some other field, some other split point, to split the data into two camps below it, to try to tease out where all those pink records go and where most of the blue records go, and so forth. So you can keep doing this and doing this to smaller and smaller subsets until either you found a useful pattern that could perfectly predict, say over here, this pattern can perfectly predict that probably all records that have a yes A, yes B, and a no C should be pink, right? Because that's what the pattern we found was. At this point, maybe this subset of records is so small that so few records have a yes A and a no B that even though most of them are pink, there's so few of them, maybe that's noise, or maybe that was just random that they happen to mostly be pink, right? So something to keep in mind. Now, the nice thing about classification and regression trees, the big advantage over k-nearest neighbors, is you can visualize and see this tree, and you can actually understand patterns from this. That is, you can actually read off records with a yes according to condition A look like this. Records with a yes for B look like this, and those records tend to be pink, right? You can understand that pattern by visualizing it off this tree. K-nearest neighbors has no such pattern description like that. All right, so let's see an example of classification and regression trees. So for this example, I'm going to use a different data set. It happens to be a data set that represents people in, I think, some club or something like that, and whether or not they donate to a cause. So these are potential donors to some cause. And in the end, we have a field, I think it's called target B out here, with a value of 1 or 0 representing whether or not they donated. Okay, so the 1s are donors, the 0s are people who don't donate, and all these other fields are just different pieces of data we know about them, like the number of children they have, whether or not they're a homeowner, I think household income, but it's categorized into, I think, 1 of 5 categories, genders, wealth, and so forth. I think these are home values and other things like that. So we have all this information about something like, let's see how many records there are, 3,120 records, and we know whether or not they were donors or not donors. So we were going to use the algorithm, classification and regression tree, to see if there's a pattern to understanding who donates and who doesn't. Okay, so if we're trying to understand a donor from a non-donor, that's classification, right? It's 2 categories. It's not a numeric thing, because you can't be a half donor or a 3/4 donor. You're either a donor or not. So it's a category thing. So first thing, partition. Always partition. And again, for whatever reason, this particular data set has 2 fields at the beginning here, which are ID numbers. One of them is just a sequential number, 1 through 3,120, and the other is some other identifier, maybe their ID number or attendee number or something like that. I'm going to leave those pieces of data out of the partition because they're not useful for determining who donates and who doesn't. There's also a field at the end which is the amount they donated. So we could theoretically predict that, but I'm just interested in predicting who donates and who doesn't. For that purpose, I don't want to include how much they donated, okay? Because obviously if they donated anything above 0, they were a donor, right? So if I included this field in the pattern or in the algorithm, it would easily find that, hey, anybody who donates more than $0 is always a donor. That's a pattern, but not a useful one. Because if I know how much they're going to donate, by definition, I know who donates and who doesn't already. Okay, so I'm leaving that and the ID fields out. I'm going to go with a 60-40 split. as default. And there we are. Now in this case, classification and regression trees require numeric data. All of this data happens to be numeric. If for some reason some data was not, just to show you how this works, you can go up to the data analysis ribbon and there is a transform button. And so if I had categorical data that I needed to make numeric, then I would want this option of transforming categorical data, and I would do the dummies, the pattern or the technique we call dummy variables. And literally, if I create dummies, it would ask me what field, what categorical field are you wanting to transform. So let's say, just for example, it's the number of children. Okay, so it did that work for me, and it turned out there were 5 different categories for numbers of children. People who had 1 child, 2 children, 3, 4, and 5. So it created 5 dummy variables, and every record has a 1 for one and only one of those fields, and a 0 for the rest, right? So this first record was somebody who had 1 child, not 2 children, not 3 children, not 4 children, not 5 children. Let's see if we can find one down here. There we go. So this particular record was somebody who didn't have 1 child, didn't have 2 children, they had 3 children, not 4, not 5. So again, we just created dummy variables for every possible category, even though technically that field was already numeric. Okay, but that's how you could transform something. So I'm going to delete that tab and go back to our data partition. All right.
What was that under again?
So to do that, I went to the transform button, and in this case, I was wanting to transform categorical to numeric. So transform categorical data, and the technique we'll always use for this class is dummy variables, so create dummies. If I had numeric data that I wanted to transform to be categorical, if you remember we called that binning, here's the option for that. Bin continuous data, continuous meaning numeric. Okay, and literally it would just ask you pretty much the same thing. What field, numeric field, are you wanting to bin? And then it would ask you what are the ranges basically that you want to bin it into. You could either say I want 5 ranges that are all equally spaced, so it would figure out the minimum value up to 1/5 the way to the maximum, 1/5 to 2/5, and so on up to the max. It would equally space them, or you could even tell it I want to evenly divide all records into 3 categories. So I want whatever split it takes to put 1/3 of the records in category 1, 1/3 of the records in category 2, and 1/3 of records in category 3. Or you could just literally put in the ranges you want. So there's multiple ways you can tell it how to bin, but that's how you would do numeric to categorical transformation. Okay, so since we're doing classification, we're going to use the classification tree under the classify button. Now, classification and regression trees is the algorithm. You'll actually see under the predict button something called regression tree. Same algorithm. Okay, whether or not it's used for prediction, or also called regression, is when you're wanting to predict a numeric result, versus classification, where you're wanting to classify or guess a categorical result. Now, there's 4 options underneath here. For this class, I'm just going to suggest if you ever do anything, use single tree. It's just saying build one tree of how to split the data up. These other ways are basically ways of saying, is it better or could it be better to build multiple trees that look different and then somehow put them together or use them together to do the actual classification. It's more complex to understand how it works. If you're interested, you can read up on it. For the purposes of this class, it's enough just to say, let's just build one tree and use that as our model. All right, and if you remember, I said there aren't really any parameters except parameters that limit how the algorithm works. So we'll start by saying which are the fields we use to find patterns, to figure out what value to predict or classify, and then what is the field that's the output that we're wanting to classify. So target B, which was a bad name for the field, but something that was already there, is whether or not they donate. And again, there's two classes, donors and non-donors. And for the lift chart, I'm interested in saying how well do we do at predicting the donors, the people who are 1 for target B. So I'll say next. We're given the option to normalize the data. It's a complex reason why you might normalize or not for classification and regression trees. Generally speaking, I would say don't. It's more useful to understand what the raw values for the split values are. You can limit the number of levels, so how many different times will it split the data, up to 7 different times on each branch of the tree. And then you can set the minimum number of nodes before it should stop splitting. And by default, I think it picks 10%. So I think I had 1,870 records. So it's saying if you find a way to split records 7 or fewer than 7 times, but you're down to only 187 records, stop splitting, because now you're just sort of splitting hairs between very small subsets of data. And then finally, you can tell it to prune the tree. That is, it might find that there's ways to split the data that does better on the training set, but actually starts to do worse on the validation set. So in that case, it might want to actually prune back and remove splits or remove nodes out of the tree and do fewer splitting patterns. Okay, so that's just that option there. So again, there's options, there's parameters. Generally speaking, I would take the defaults here unless you have a specific reason that you know you don't want the defaults. Okay, and all of these are just to limit the algorithm or limit what it does, to make it either more efficient or in some cases limit how overfit it might get. The next several set of options, we can tell it to actually print and tell us what the tree is, like what fields it's splitting and what value it's using to split. We can tell it we want the whole tree, so is the biggest tree it found, the tree that pruned down to be the best tree for the validation data, the tree that got the minimum amount of error, I think on the on the validation data. The difference between those two is not important, I guess. There's a specific reason why there's a best prune versus a minimum error, and I forget all the details of why that is. Generally speaking, they'll be very similar anyway. So I'm just going to tell it we want to see the best prune tree, and that's just simply I want to visualize what that looks like. And then so forth, we can get summary reports and lift charts for training and validation data. So let's see what that looks like. This one's taking longer to run, but that's okay. So again, what it's trying to do, and you can imagine this is a lot of work. Oh. Well, I'll be honest, that's never happened. And all the times I've taught this class. So, like I said, like I was saying, you can imagine it's a fair amount of work because it has to figure out every time which field should I split and what value should I use to split into 2 camps to get the best subsets, right? There's a lot of options, and then it has to redo that for those 2 subsets and redo that for those 4 subsets, and so on and so forth. So it's a lot of work to do. Again, it's something good for computers. They can automate all that. All right, let's go back to classification trees, single tree. prune the tree so we can see the best prune tree, and then we'll run. So, yes, question?
Quick question. When you showed us the lift chart for k-nearest neighbors, was that for the best K or for...
That was for the, yes, so the question was, when we looked at the lift chart for k-nearest neighbors, was it for the best K? And yes, it was. So it only showed us one lift chart, and that was the one it figured out was the best K, since we asked it to find the best K between 1 and 20.
So for that particular problem, even you were saying that the best, that k-nearest neighbors didn't perform that much better than the average best group.
Mm-hmm.
So for that particular problem, can we conclude that with that training set and validation set, k-nearest neighbors probably wasn't accurate at data mining out?
Yeah, so the question, just for the recording's sake, was in that case for k-nearest neighbors, the validation chart, or lift chart, wasn't very promising. There wasn't a large gap there, but it was for the best K, so overall we can conclude that no other K would have been better, and k-nearest neighbors probably wasn't a good algorithm for that case. Yes, you could probably conclude that. Now, it was better than the average guess, so it was better than nothing. And if we did happen to run other algorithms, it's certainly possible that other algorithms would have done even worse. So maybe it was the best we could do, but it wasn't fantastic. Yeah, it wasn't going to get us, I think it still was getting an error something like 26% of the time. So, I mean, if you think about getting an error 26% of the time, at least in school, that's C average work, right? Maybe that's okay, maybe that's not, but that's a pretty high percentage error, generally speaking, without knowing the actual problem that much. 26% of the time getting it wrong seems like a pretty big chunk.
Depends how much money's riding on it.
That's, yeah, so the comment of depends on how much money's riding on that, and yes, it does. Depending on the problem and the situation, that might be perfectly livable. Other situations, maybe that's not acceptable in any way. Okay, so we did get the k-nearest neighbors to, or I'm sorry, the classification and regression tree to work. Again, it's going to tell us sort of the options we selected. It's going to tell us, let's see if I can get to scroll. So it actually worked out that half of the people donated or didn't donate, half of the people did donate. Okay, so again, if we were going to do an average guesser and we'd just randomly guess, we'd expect to get it wrong half the time, right? Either we'd guess everybody donates and get half of them wrong, we'd guess everybody didn't donate and get half of them wrong. So with that as a baseline, you can see here, this is it's called the training log. It's building the tree. It says if I don't use, or if I use 0 decision nodes, that is, I just make pure guesses, I get it wrong pretty much 50% of the time. It rounds up to 50, right? If I use 1 node, that is, I just say, okay, for 1 field, I'll split all records based on that 1 field into 2 camps, and then I'll guess based on which camp you're in, I get it wrong 43% of the time. So an improvement, and so forth. So if I use more nodes and more nodes, more ways to decide and split the data, eventually my error's going down and down for the training data, right? Because eventually I can find ways to split all the training data into perfectly homogeneous subsets, even if they're only a subset of 1 record. So the key is now it has to figure out, well, this is that full tree, the maximum number of nodes. I think I said I can only split 7 times at the maximum, so it couldn't split everything down. And the best it ever got was 37% error. Okay, and here it will tell you what those nodes are. So it first split on whatever max RAM int field is, and it used a split value of 13. So values less than 13, values greater than or equal to 13, I think. And it split those into 2 camps, which now it decided between those two, one of them split on their last gift, if they donated before, how much, and the total number of months, I think, since their last donation, and so forth. So it kept splitting and finding ways to split nodes. Finally, we can see down here the best prune tree, so using the training data to classify the validation data, the tree that did the best was one that only split one time on one field. Okay, that was the best we found we could do. And you'll see down here the overall percentage error we got on the validation data was 45%. And you can see that broken down into, it guessed the donors wrong 49% of the time, the non-donors wrong 42% of the time, for a total of 45% error. So that doesn't sound very good. If you could get 50% error just guessing, the best tree we found we can do still got it wrong 45% of the time. So, very small increase over average, or over just random guesses. So we can look at what the prune tree looks like, visualize what that looked like. Not very exciting since it's just a tree of one node. And we can look at the validation lift chart, which pretty much confirms what we said, which was we're really not doing much better than the average guess could. Okay? Either this is a bad algorithm for this problem, or there just really isn't a pattern to figuring out who should donate and who shouldn't, or who does donate and who doesn't, given the information we have about, you know, what zip code they were from, household incomes, stuff like that. It's possible a different algorithm could have done better. Okay, generally speaking, you'll want to run, in the real world, you'd want to run multiple algorithms. Okay, maybe with different parameters, different runs with different parameters, to try to find what would work best. Okay, in this case, running this one algorithm on this one data set with one set of parameters, we would conclude, you know, there really isn't, it's not doing any better than just a random guess would. You know, it's really not a useful application of a data mining algorithm in this case. Okay, we really are pretty close to out of time, but I'm briefly going to go back and talk about one more data mining algorithm. It's very simple to understand. It's called multiple linear regression. It requires numeric data, and it can only predict numeric data, because literally it's just a very simplified numeric equation that just multiplies every field. So every numeric field multiplies its value by some coefficient, and then sums up all of those values, all of those multiplied values, to make a prediction. So literally it says, if I'm trying to predict field T, the numeric value for field T, I'm just going to try to find an M0, M1, M2, M3 values that minimize the error of this equation. That is, how off this prediction T prime is to the real T value in the data. So it's linear regression because it's just a linear equation of summing up the multiplication of values. Okay, very simple. Visually, it would look something like this. Now, this is a linear regression line, so a linear line trying to fit this data, which is a data on two axes, right? Generally speaking, right, you'll have maybe dozens of fields, so it'd be a dozen-dimensional space that is trying to find a flat surface in that space to help predict values. Okay, and again, the slope of this line, where it intersects the x-axis or the y-axis, and the slope of this line is determined just to minimize the error of all the predictions. So obviously, this line would be better than a line down here or a line like this. Okay, so it just found what linear line in this space minimized what value it could predict for all these blue dots. So it's just trying to average through the blue dots. Okay, that's multiple linear regression. It's run the same way. So if we opened Microsoft Excel and we went back to this same data set, since it's all numeric, we would use the predict, and we would select multiple linear regression. There really isn't any oh, selected the wrong sheet. Data partition. There really is not any parameters to multiple linear regression. technically, I guess this is a categorical field, so it wouldn't make sense to try to predict a numeric value for it. But the only true field, or the only true parameter, is whether or not you force the constant term, that M0, which isn't multiplied by any other field value, if you force that to be 0, or if you let that be something greater or less than 0. Generally speaking, so that's really the only parameter, generally speaking, you would never check this box, force this to be 0, unless you had prior knowledge that that's what you wanted for some reason. The specific problem called for a numeric prediction of 0 if all the field values are 0. Okay, then you would want to force this to be 0. Otherwise, you wouldn't. Same thing, you can get summary reports of the error percentages and lift charts and everything else. The rest of all this stuff up here is just printing out effectively statistics information about why it chose the M values it did and how it minimized things, and statistically how likely these things are to be changed in any way, and so forth. Nothing we would need to do with any of those. The only other, there is one more thing you could do, which is variable selection. If you wanted to say, I only want you to use a certain number of fields in that linear equation. I want you to find the 5 best fields to multiply and use to predict something, instead of trying to use all of them. Again, that's probably not useful unless you have a specific reason why you would want to do that. Okay. Now, what you may find when running multiple linear regression is it finds very small value, M values, to multiply by a field, which probably just tells you that that field isn't really useful for prediction, because we're basically almost zeroing it out by multiplying it by a very small number. If that's the case, that can at least help you identify a pattern to say which fields are important for prediction and which fields were, unimportant and could be zeroed out, and the equation would be pretty much the same. It's not going to give you a pattern nearly as concretely and specifically as classification trees would, which would literally tell you here's what field you should look at first and what value you should split records on to try to divide them into 2 homogeneous sets and so forth. Okay, that's data mining. There are other algorithms we did not cover you might want to learn in your own time, which certainly not expect you to use them on the homework assignment or know about them in any way for the exams. So that's it. Next time we'll talk about forecasting. We'll go into optimization. The first assignment will involve using an Excel spreadsheet. I'll provide it for you. It's one they'll provide with the book, and it'll literally be just applying one or more data mining algorithms like we did tonight to that data. Likely, you will need to transform the data in some way, so you'll need to understand if I'm using k-nearest neighbors, I have to transform categorical data to numeric using the create dummies method, right? And then always remember to partition the data and base your analysis on the goodness of the algorithm on the validation data errors or the validation data lift chart. Okay, so that will be the assignment, just applying the algorithms and then verbally or written tell me which algorithm did better and briefly why you think it's better. Lower percentage error, better looking lift charts, whatever that means. So there's really not much to do for assignment 1. If you followed what I did tonight, or if you look it back up on the video, you can see literally the steps. It's basically just clicking buttons in Excel once you've installed the software. Again, there's a PDF on Blackboard explaining how to download and install the software. Be sure and follow those directions explicitly so that you get the software with a license to run for more than 14 days. Otherwise, come week 3, you'll no longer be able to use it. Okay. All right, I will see you next Thursday, 6 o'clock. If you have any questions, feel free to email me. Thank you.